I've got a question about that game we were just playing.
Oh yeah, that super cool, not nerdy at all game of atoms.
Yeah. Well, in the middle, I was pretending to be an electron.
As you do, yeah.
And someone knocked me out of my shell.
Out of your shell?
Right out of it.
How did you do that?
I don't know. That's my question.
I think we should become detective investigators.
Okay.
Look at the evidence.
Okay, the evidence. I grazed my knee when I skimmed it on the curve, and Billy is still laughing at me now for it. That's all the evidence I've got.
How about we go into the chemistry world and think about the evidence in real atoms?
Oh, they're definitely applicable to normal people.
I think so, yeah.
So the idea is electrons can be knocked out of their shell. But how do we know it's a shell?
Well, that comes a bit later. But the knocking out of something, the removal of an electron from an atom is called ionization.
It is indeed. So it's just like it sounds. You knock an electron clean out of its orbit.
Yeah, but the atom it's orbiting has to make up a molecule that is gaseous at the time.
And it has to be, you do it with 1 mole of gaseous atoms to form 1 mole of gaseous ions in your equation.
Sometimes you have to write the equation of the first ionization of something.
To say I'm doing it for nitrogen.
Okay, so it's first ionization, you'll have your nitrogen become positive because electrons are negative, and then you'll have 1 mole of things. Of course, you should both include, they both have to be gaseous, so you have to include your state symbols as well.
And this is your first ionization energy. And the reason it's your first is because you can do it again and again.
And your second, you'll just go into 2+, and you'll again only release 1 electron. So this one sort of disappears for now.
And these still gaseous. And this can carry on, this can keep carrying on.
This can go on for a while. But there's a few things that affect how much energy is required to do this.
Yes. The first thing is how close the electrons are to the nucleus.
This is called atomic radii.
Exactly. So if we draw it in the simple model, it's not exactly like this, but if that's the nucleus and you've got these electrons whizzing around, it's not exactly like that, but the radius here is going to affect it.
So if they're further away, the proton will have less effect on the electrons.
Exactly, it'll have less of a pull. Therefore, it'll be easier to knock it off. Imagine a school teacher with lots of students around them. The student's really close to the teacher, they can keep an eye on, they can say, oh, stop wedging him. But the students way over there at the other side of the playground are going to be harder to control by that one teacher.
Yeah, that's a good analogy.
So that's why the radius affects it.
Then there's shielding. So, for example, other electrons can be in the way of the other electrons, which prevent charge from the proton reaching them.
So the idea that there's 2 on the inside and then there's even more electrons on the outside. If you're trying to knock off one of these electrons, this is repelling it out. This has got some shielding on it. But if you remove the electron, there's less shielding for the rest.
Yeah.
So it's going to be easier to knock it off with each thing you've got rid of.
And then finally we have just repulsion of the electrons themselves.
So if this electron's back here, these are both electrons in there, but they're in separate shells.
So they're being repelled from each other.
Both negative. So this will make it. This sort of relates to it being a larger radius. It's pushing it further away. So although the nucleus is pulling it in stronger than the electrons repelling it, it's still making it slightly easier for someone to come and grab that electron.
And the last thing that affects it is nuclear charge. If there's loads and loads of protons and say 1 electron, not this will happen very often, that would be pulled in a lot, so you have loads of energy to remove it.
Exactly. So if we look at this example, we've got nitrogen. Just made that off the top of my head, you can do it for anything. It's gaseous. So it's lost 1 electron, which has been fired off. So let's say this had energy 200. That might not be very accurate at all, but let's just say it had energy 200.
Yeah. So once its electron is released, it still has all the protons. So you have less electrons, same amount of protons, all of them are being pulled a bit more.
Yes. So that means the radius is going to be smaller, the shielding is going to be greater,
and the nuclear charge to electron ratio will be higher. So this will be perhaps higher, even up to 400.
Yeah, it's going to be much higher energy. And this can keep going, it's going to be more and more energy each time. But is it going to go up, say, 200 at a time? 200 is a made up number, but 200 at a time.
It won't go up uniformly, and also there'll be jumps, and this is what helps us prove the existence of shells.
And that's what the ionisation energy is all about, really.
Yeah.
It's proving the existence.
So if you have annexes, and we're going to use, I think we should use magnesium.
Can do, yeah, magnesium's pretty close.
So you use magnesium as it's a group 2 element, so when it gets past group 2, we're saying that it's going to leave a shell.
Yeah, so this is the energy required, is up here. The energy required to knock it off.
So then we have our magnesium stems.
Yeah, that's going to be essentially naught on this.
So first ionisation.
That will take X amount of energy. And then it's essentially in the sodium column. It's not, you can't really think of it like that, but you can sort of picture it as being in the sodium ion. So everything's pulled closer together, it's going to take more energy. Because if you've got the nucleus, you've still got this inner shell, and then it's the next shell. It's lost one electron, so it's pulled in closer, as Triv said with the nucleon number, the electron number. It's going to be pulled in closer, so the energy's going to increase.
But now, when it loses an electron,
You've lost that entire shell, you're going to a different shell.
and we know this because it's going to fly up. It's going to be a huge change in energy, and that's because of the massive change of shielding from the shells. So then our huge jump will show that there's been a change in shell. And you can use this to predict what element or group your element was in by how many ionisation energies it's undergone.
So this has helped us to show the shells, how many electrons are in each shell, and how the shells work. And that's what it looks like. And then in the next shell it will carry on going
go
up,
up a little bit
and so on.
until it reaches the next shell it jumps.
And that's ionisation energy.
Yeah.
Pretty much done with this one, so let's go on to the next video, I think.
Alright.